Hi, my name is Alia Sidaliva, and I am here today to discuss integrals, specifically definite integrals, and how we can find them using graphing calculators. Now, before we get into the actual calculating part of integrals and how we find them, it's really important for us to understand what integrals are. So integrals are essentially the area underneath a graph going all the way to the origin. And so this is incredibly important for us to know because it has a lot of real life applications and it's just very, very useful. And so first we can look to a theoretical example just to see how integrals work first, and then we can actually apply it to a real world problem. So the first one that I want to do is one that's really, really simple, one that will be very easy to grasp, and that is for the equation of y equals x. Now y equals x is the parent linear function, and so it's very, very easy for us to graph and understand how integrals work. And so first and foremost, we have to ensure that we are actually plotting the graph so that we can have a visual representation of what an integral is. And so we are just going to plot this graph. Our y-intercept is going to be the origin because there is no y-intercept, there is no b for us to actually plot, so it would just be 0. And then our gradient here is just 1, since there's nothing in front of x. That just means it's 1 times x. And so we are just going to plot this as a regular gradient. 1, 1, 2, 2, 3, 3, just going on as needed. So we can really see that this is a gradient. So we can really see that this is a linear line. We can just continue it on and on and on. Just make it a little easier here. There we go. And then, of course, adding in our arrows, since this is a graph that does continue on, since we don't have any restrictions or anything like that, it does continue on forever. Now, in order to understand an integral, we first have to define where we want to find the integral, and this is called a definite integral. And so it sounds very self-explanatory. Basically, you define the values that you would want to find the area for. And so we do this through the x values. So, for instance, within this graph, I want to look at the values between 2 and 6. So we're only going to be looking at this area here. And so, as I stated before, an integral is the area from the line itself to the x-axis. And so that is incredibly important for us to understand because it's not the area underneath the entire graph, it's just to the origin. And so if we wanted to find like the gradient, or not the gradient, the integral between -4 and 8, it would just be this area here. It would just be this general area here. But for the time being, we're not going to worry about that, and we're just going to worry about this area here. And so in order to do this, we could, of course, just do it from a visual standpoint. We could break this up into 2 different shapes of a triangle and then a rectangle and find the area that way. And this does work for linear lines. However, when we get into more complicated graphs such as quadratic graphs, cubic graphs, and like other graphs along those lines, we're not going to be able to do that. So it's important for us to understand how to do it from a graphing calculator standpoint. And so the first thing that we need to do with the graphing calculator is, of course, turn it on and clear out any work that we had been doing previously. And in order to get to the place where we can actually calculate the integral, we need to go over here to this button called Math, and we stay under Math, and we just go all the way down to number 9. And now we're presented with this. Now, in order for us to actually get the correct integral, we have to understand where to put everything within our graph. And so for this particular problem, we're only looking at 2 and 6. And so these are our restrictions. And this is what we're going to put in these two boxes following this like curvy, almost F looking letter, but it's not really a letter, it's just a symbol. So the lower end will go on the bottom, so 2 will go here, and then up here we will put 6 because that is our upper restriction. Ooh, it did not. There we go. Then in the parentheses we are actually going to put our equation. Now our equation this time is just x. So you just put that in there and you're done. And then over here to the right of D, what we want to put here is the variable in which the equation is being measured. And so in our case, it's x. If it was t or v or literally any other variable, it could be like f of v equals v squared plus 1, then you would put v after d because that's the variable that you're measuring everything in. And so then after that, you just press enter, and we get 16 as our number. So our integral equals 16. And so that is our area under this graph. And this can be used for many, many different things. The first primary thing that a lot of people use this for is within physics, because when you take the integral of a linear line for a graph that is time versus velocity, then you can actually find the acceleration of a system, which is incredibly useful when it comes to physics and just the various equations that you need to be able to use, and if you are just trying to solve the problem and trying to solve for acceleration. And so we can actually do one of these problems. And so let's just say that our x-axis is time, and our y-axis is velocity. And we'll do velocity in meters per second and time in seconds. Whew. Do not know what happened with that parenthesis there. And so now let's just say that within this problem, our function for velocity equals time squared plus 1. And what this plus 1 signifies is that at the time at which our project or experiment was being taken, it was actually already moving at a speed of 1 meter per second. And so we'll just go ahead and graph this very quickly so that we have a visual representation of whatever it is that we were trying to find. And then we can just draw in the line because I don't think that I would be able to actually use the linear lines that I had been trying to use before. And so not the most perfect graph, but we can understand the point. This is a quadratic graph that is really, it would be very hard to find the integral of. And so, as I stated before, the integral of a velocity time graph would give you the acceleration. And so, let's just say that we wanted to find the acceleration between -2 and 2. And so, in order to do this, we would have to go back to our graphing calculator, our handy-dandy graphing calculator. And so we would just clear out any previous work that we had done, and we would just do the exact same thing as we did before. We would take math, go all the way down to 9, put in our lower restriction, which is -2, put in our upper restriction, which is 2, and then enter in our actual equation. And so, for our sake, I'm just going to make t equal to x, because that is just a lot easier, and a lot of times when we look at graphs, it's always in terms of x. And so, let's go back over here. So, t equals x. And so, our actual equation, when we substitute x in for t, would be x squared plus 1. Now we can go back to our graphing calculator and actually enter that in. So we go up to this key over here where you can actually put in your variables, which is x, and then we use the little caret key to put in a exponent. And then whenever you do exponents, you always have to use this key over here in order to get it out of the exponent, so that you don't do like x to the power of 2 plus 1, because that would not be what we actually need to graph. And then we would go over to D and just put in x, because we are measuring this in terms of x once we substitute x in for t, just because it's easier that way. And then when we enter it all in, we find that the acceleration is 9.33. meters per second squared, just because meters per second squared is the unit that you use in order to, in order to do that. And so we can really see that integrals are very fascinating, and they're incredibly important when it comes to physics and when it comes to many other real-world applications. And so now we know how to use a graphing calculator to find the area underneath a graph between 2 points, which, as I mentioned before, has many applications, such as in physics and various other areas of science. And so thank you very much for listening to me, and I hope that you have a great day, and hopefully you learned something new. Thank you very much.